We have been discussing planes in three-dimensional space. If we have a plane in three-dimensional space, we know that it can be described by a vector normal to that plane. In this case, the components of this vector normal to the plane has components A, B, and C for the x, y, and z components respectively. This plane can also be described by a point within the plane. This point we will call point P naught, and P naught or P0 has coordinates x naught, y naught, and z naught, and this is as the plane is described in an x, y, z coordinate system. Given a point in the plane and a vector normal to the plane, we have seen that the standard form for an equation of a plane is given as the x component of the vector normal to the plane times the difference in position between a point on the plane, the x coordinate of a point on the plane, and the x coordinate of another point we're interested in. We will say this point right here, we will call this point point P, and point P, this arbitrary point in the plane, has coordinates x, y, and z. So that means then that the second term has B being the y component of the normal vector normal to the plane, times the difference between our point P's y coordinates and our point P0's y coordinate, plus C, z minus z naught, where C is just equal to the z component of our normal vector to the plane and our z component of our point P0. Let's move this a little bit more to the left. There is more than one way to express an equation of a plane. An alternative way of expressing an equation of a plane is to express it by separating out the x, y, and z from the known point x naught, y naught, z naught in the plane. For example, let's distribute each of the coefficients through each of our terms. Ax minus ax naught plus by minus by naught plus cz minus cz naught is equal to 0. So we have constant terms and terms that are not constant. The constant terms are ax naught, by naught, cz naught. Let's group those terms and move them to the other side. The left side of the equality has ax plus by plus cz, and the right side of the equality now has ax naught plus by naught plus cz naught. This expression on the right side is just a constant. This constant is the sum of the products of the components of the normal vector and the coordinate of our known point in the plane. We will call this D. And with D, we can now express another form for an equation of a plane as ax plus by plus cz is equal to D, where D is that constant term that we pulled out involving the components of the normal vector and the coordinate of our known point in the plane. What does that D do? By expressing a plane in this form, D and different values of D correspond to different planes that are parallel to each other. For example, if d is equal to 1 and the normal vectors have the same normal components for simplicity, d equals 1 would be a plane that is different than d equals 2. If d were equal to 3, that would be a plane different than the planes given by d equals 1 and d equals 2. But what's shared by all of those planes is that they have a normal vector that is parallel to the normal vector in every other plane, which means that those planes are parallel to each other. So the normal vectors of parallel planes have the same direction, and expressed in this form, we could see that different values of d would give us different values or different parallel planes with the same set of normal vectors. Let's do an example where we have to find an equation of the plane that passes through the given point and is parallel to the given plane. Well, the given plane has an equation given by 2x plus 3y minus z is equal to 4. A vector that is normal to the plane is given by the coefficients of the variable terms. So this vector we'll call n vector is equal to a for the x component of the normal vector, b for the y component of the normal vector, and c for the z component of the normal vector. For two planes to be parallel, they should have the same set of normal vectors that describe them. Therefore, for our parallel plane, we just need a point, and we're given a point. I'm going to call this point P naught to be consistent with the notation that I've been using. And P naught has the coordinates 3, 6, and minus 2, standing in for the x naught coordinate being 3, the y naught coordinate being 6, and the z naught coordinate being minus 2. The standard form of the equation of a plane will allow me to construct an equation for our plane. Let's plug in the values we have for this standard form of the equation of the plane. A is equal to the coefficient in front of the x term in our given plane. So this will be 2x minus x naught, which is 3, plus b, y minus y naught is 6, plus c, and c is equal to a minus 1 since it's the coefficient in front of our z variable. So this would be minus 1 z minus a minus 2, where minus 2 is equal to z naught. Therefore, an equation of a plane that is parallel to the plane we were given is described by this standard form for the equation of the plane. I want to point out that the problem says find an equation of the plane that passes through the given point. There is an infinite number of planes, or let me rephrase that. There's an infinite number of equations that describe this very same plane. For example, what if our normal vector was, we'll say, had components 1, 3 halves, minus 1 half? that would also describe the same plane, because this would just have a normal vector that is scaled 1/2 to the normal vector of the given plane. Let's go ahead and express this equation of the plane in the alternative form that we've learned about previously. An alternative form for expressing an equation of a plane is ax plus by plus cz is equal to d, where a, b, and c, again, are the components of a vector normal to the plane. And in this case, d is defined as the constants that we pull out from the standard form of the equation of the plane. So d would correspond to that. But I don't like to memorize formulas. This is another formula I have to put in my head. This d equals ax naught plus by naught plus cz naught. So instead of just plugging into this formula, let's pretend we did not know this formula. That formula exists, but why hold something else in your head when you can just do a little bit of algebra? So that's what I'm going to do. I am going to put the standard form of the equation of our plane into this form. And to do that, I just have to distribute the coefficients. So that's 2x minus 6 plus 3y minus 18 minus z minus 2 is equal to 0. This is 2x plus 3y minus z is equal to 6 plus 18 plus 2. This is now 2x plus 3y minus z is equal to 26. This is an equation of the plane that is described by the given point and by the vector normal to another plane in which it is parallel to. Notice these two equations, the one equation with the plane that we were given and the other equation with the plane that we generated. Notice how those two planes have actually the same expression for the normal vector. The normal vector of each of these planes are the same. Or let me rephrase that. The normal vector for each of these planes have the same components. X component being 2, y component being 3, z component being minus 1. But notice what's different. The quantity on the right side, that constant. In the plane we were given, the constant was 4. The plane we just generated the equation for, the constant is 26. Since these two planes differ only by a constant, we know that these planes are indeed parallel to each other, where one is above the other plane, separated by some distance.